Good afternoon. My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University and the Buchanan Chair holder in the Zachry Department of Civil and Environmental Engineering. We added environmental since last time, so we changed our name a little bit. Welcome to the 27th Buchanan Lecture, which started in 1993 when Ralph Peck gave the first lecture. This year's lecture is again sponsored by a generous gift from Fugro. Matt Van der Veen is the CEO of Fugro, represented today by Anwar Akhtar. Thanks to Fugro's sizable support, the Buchanan Lecture remains free of charge to all participants. Thank you, Anwar. I also want to recognize those who have sponsored graduate fellowships in geotechnical engineering. Todd Soboda, Patrick Baecher, and the Terracon Fellowship. Willie Bowman, his wife Mildred, and the Bowman Fellowship. Mark Balus and the Balus Fellowship. Alan Young, who created the Don Murph Fellowship. ECS, with Mark Zartman and the ECS Fellowship. And this year we added 3 Darrow Hooper Fellowships. You know that Darrow was the reason for the start of the Buchanan Chair. So without Darrow, we would not have the Buchanan Lecture. And Darrow passed away last year. We'd like to continue to raise more funds for fellowships to support our geotechnical graduate students. These funds go a long way to help them. For example, a competitive fellowship of $1,000 allows an international student to get in-state tuition, which lowers their cost by some $6,000 annually. So your $1,000 gift has a 7-fold return and a tremendous impact on their lives. I also want to recognize the students, both at Texas A&M and at UT and other universities. Prominent visitors, we have Gregory, past president of GI. Where's Gary? And we have Bob Gilbert, also on the GI board, chair of the UT Department of Civil Engineering. Thank you. Our invited speakers, of course, Greg Baecher and Rudy Bonaparte, and my colleagues in geotechnical engineering, Chuck Albany, Marcelo Sanchez, Zeno Medina, and our new recruit, Anand Pupala. Where's Anand? I've known Anand for many years. He's, of course, a great geotechnical professor and engineer, but I know him as well as unassuming, politically savvy, and extremely efficient. So welcome to Texas A&M. I also want to acknowledge another special group, and that is the board of SERGEP, the Consortium for Education and Research in Geoengineering Practice. We started that about 2 years ago out of frustration to hear practitioners say that our research was useless to them. SERGEP now has 11 member companies and growing, and I want to thank them for their proactive impact on practice-oriented research. The chair of the board is Shailendra Enley with Intertech, and the vice chair is Todd Soboda with Terracon. The companies are Intertech, PSI, Terracon, Fugro, Gorondona, Hayward Baker, Maynard, Trevi Icos, Paradigm, A.H. Beck, ECS, and Rabba Kistner. So if you wish to join the SERGEP group, please talk to me or Shailendra or any SERGEP member. I also want to recognize Blake Thurman. He's probably in the back there taking care of the front desk. Blake Thurman, for my assistant, who's been working long hours to help me organize this lecture. Please sign the guest book, which is circulating, name and email. This is how we build our mailing list to tell you about next year's lecture. This is particularly important for the students in my class, as I give 5 points on the final exam, not the final grade, for attending the Buchanan Lecture. The best way to find out about next year's lecture is to go to the Buchanan Lecture website around September of each year. We always host the lecture around the latter part of the fall. Since I got elected president of ASCE 2021, thank you for your votes, by the way, I wish to take advantage of this opportunity to say a few words about ASCE and urge you to be a member of ASCE if you're not. Why should you be a member of ASCE? Many reasons. Obviously, I'm a little bit biased. Number one, it's a good financial deal. The dues are $245 per year, and you get many advantages, like 10 professional development hours. If you're not a member, you would have to pay $1,590 for those 10 professional development hours, which are required for you to maintain your PE license. Another financial advantage, the difference in the conference registration is typically $150 lower if you're a member compared to not a member. So 2 conferences, you pay for your dues. You get a 75% discount on the journals. The list goes on. But the main reason for being a member of ASCE, in my opinion, is because it's your professional family. You know, in life we have 2 families. We have our blood family and we have our professional family. And you would never think twice about helping your blood family. You know, your children, your spouse, your parents. We should react the same way when it comes to ASCE, which is our professional family. Imagine for a minute that you have a 6-year-old daughter, and she asks you for an apple. Would you step back and say, wait a minute, what's in it for me? That's unthinkable. You would very likely give the apple and say, not only that, but I'm probably going to continue to save money so you can go to university later on. Well, the apple for ASCE is the dues. And the saving for college is getting involved as a volunteer, getting engaged. So if you're a member of ASCE, you're part of my family. And as such, you have family privileges. If not, please become a member of ASCE as soon as you can. Be part of our professional family and get engaged. So that's the end of my commercial. Now the program. In a moment, I will introduce Dr. Greg Baecher, who will deliver the 2019 Buchanan Lecture. Questions will follow. Then I will introduce Dr. Rudy Bonaparte, who will deliver the 2018 Terzaghi Lecture. Questions will follow. Then we will take a photo on the stage, and then we'll end the afternoon with a reception at my house. And maps are on the front desk, so you know how to get there. Now it is my pleasure to introduce Professor Greg Baecher. Dr. Baecher is the Glenn L. Martin Institute Professor of Engineering at the University of Maryland. He holds a bachelor's degree from the UC Berkeley and a Ph.D. in Geotechnical Engineering from MIT. He's the author of 6 books on risk, safety, and the protection of civil infrastructure, and 200+ technical publications. He's a recipient of the USACE Civil Engineer, Corps of Engineers Commander's Award for Public Service, the Panama National Award for Science and Technology Innovation, GeoSNet Distinguished Achievement Award for contribution to geotechnical reliability, and is a member of the U.S. National Academy of Engineering and of the UC Berkeley Academy of Distinguished Alumni. More personally, I know Greg as a mathematician, a philosopher, a brilliant engineer, and a humble person. The title of his Buchanan Lecture is Putting Numbers on Geotechnical Engineering. Please welcome the 27th Buchanan Lecturer, Professor Greg Baecher.
Jean-Louis, thank you so much for inviting me. Thank you. It's been a very pleasant time today. This is my first time in College Station, and it's been delightful. So thank you all so much. It's my great pleasure to be here. People have talked about geotechnical judgment for a long time. The great one himself had a whole series of papers on this topic presented before the Boston Society of Civil Engineers some years ago, some decades ago. Arthur Casagrande wrote a famous Terzaghi lecture on this topic, and Bob Whitman followed up, as many of you are probably aware. Steve Vick wrote a whole book on this topic, and if you haven't read Steve's book, it's excellent, and I highly recommend it. And most recently, my longtime and very good friend, Alan Marr, gave the Seed Lecture this April on the topic of engineering judgment. And it was actually Alan's lecture that I was able to attend in Philly in April. It sort of led me to think about this topic. And when I think about engineering judgment, and it's the miracle of engineering judgment in our profession, most people talk about it qualitatively. But I love this quote from Edwards Deming. Without numbers, you're just another person with an opinion. And so my question this afternoon is, so if we're going to put numbers on engineering judgment, how do we do it? How good are we at doing it? And we've been trying to do this for about 50 years now, which is kind of astonishing, but we have. And the question is, have we learned anything over this period of time? And I'd like to take you through a series of little case history vignettes to make a few points, and I hope they will be of interest to you. I hope they'll be, in some cases, humorous, but I also hope that they will be little nuggets to crystallize your thinking about this undertaking. So dam safety. This is and many people in this room have been involved in dam safety. Rudy has, I have, a number of others. I like these quotes. This is from the IPCC. This is the Intergovernmental, whatever it's called, Panel on Climate Change. This is the UN-sponsored group of people that's been working on climate change modeling. And so they come out with these sorts. This is an Associated Press quote. They say that we can now say with extreme confidence that something, something, something. We can now call it extremely likely that something, something, something. What do these terms mean? I mean, what does extremely likely mean? I was sitting this morning in the restaurant reading that greatest of all American newspapers, and it was talking about probability in jurisprudence and how the question was on admissibility of evidence and whether it had a likely probability of changing the verdict. What's a likely probability mean? So the IPCC, as you know, is a kind of a controversial area, and they have come out with a set of recommended terms, which in the business, these are called, I didn't make this up, words of estimative probability. They are basically adjectives and adverbs that we apply to things like the event is likely to happen. It is very likely to happen. And the IPCC has come up with this table that they would like all of their scientists to use so that when someone says it's extremely likely, well, they don't have extremely likely there. If one of their scientists says it's very likely, that means about 0.9. Right? That's nice. The Corps of Engineers beat them to this by at least a decade. This is the Corps of Engineers dam safety verbal mapping scheme for translating adjectives into numbers, and that looks pretty much the same. This is Steve Vick's book. This was heavily influenced by Steve some 15 years ago. Well, take a look at the first one, virtually certain. Well, it's only an order of magnitude different, right? What's an order of magnitude among friends? But the Corps uses this as a sort of a starting point. The news is so good these days you can't make it up. So this is not ancient history. This is September 24th, 3 weeks ago. The Pope advises us not to use too many adjectives in our writing, and so we might take that as a rule for this afternoon. These words come actually from this guy, Sherman Kent, who's relatively famous in the subjective probability business. He was a member of the OSS during the war. He was a professor of history at Yale after the war, and then he was the sort of the senior intellect at the CIA for decades afterwards. Kind of makes you feel humble in your accomplishments. But he, for years, pushed the CIA and its intelligence analysts to not use adjectives, but to use numbers when they were advising the president or when they were, so the morning intelligence briefing, whatever they call it, that they give to the cabinet and to the president. This was only sort of successful. The agency analysts never really picked this up a lot. But in preparing this lecture, I noticed that as recently as 2015, the Office of the Director of National Intelligence, the DNI in Washington speak, issued an update to these words of estimated probability. So presumably the CIA is still following this direction. Here is an interesting plot, and this has been replicated many times. This comes from the New England Journal of Medicine, but there have been a bunch of others. And the vertical axis over there is various adjectives and some adverbs to describe the likelihood of events, and along the horizontal axis is the corresponding probabilities. And so there's sort of a general trend, and if you read through the words, it sort of makes sense that they would sort of have this increasing trend. What is more noteworthy, though, are the big black bars. Those are plus or minus 1 standard deviation from the median, and the dots are the ranges. And you can see that for some of these terms, there are 30, 40% differences in what people mean by these terms. It turns out that most of us are relatively consistent in how we use these terms, but across different people, we're not consistent at all. So I've created these blue slides which summarize what I think we've learned from each of these examples. This is the example from dam safety. You probably know the Gary Larson cartoon over there, but this is such an appropriate cartoon for what we've learned about words of estimated probabilities. The adjectives are really poor substitutes for numbers. That's the first thing we've learned. They mean different things to different people, sometimes quite different. They mean different things to the same people in different situations. They mean different things to experts and to other stakeholders. And they mean different things to dogs and to dog owners. And we also learned that we should avoid, the term of art is weasel words, and these are they. It turns out that these words tend to add more confusion to communication than they add clarity. And so in our presentations and our reports, we should tend to avoid these kinds of words because they may cause more problems than they solve. So that's what we've learned about WEEPs. Let me go back in history to the late 1970s. I was a young professor at MIT in those days. And I called this primal guessing because this was a project that involved Bob Whitman and Alan Marr and Meshach Yegian, who is at Northeastern University. Jean-Louis knows this as the origin of what we would call FN charts, but he calls bubble charts. This was an interesting project, and we learned really a lot from it. This is the Tonin refinery and tank farm in Kawasaki Bay in Tokyo. Those tanks are really big. I guess we're in Texas, so everything's big, but those tanks are really big. They're 50,000 kiloliters. So that's about, I did a calculation last night, that's about enough oil to flood a soccer field 10 meters deep. So they're big. And around each one of those patios is a firewall in case they leak, and between the patios are underground drainages in case there's not enough capacity. And around the entire site, you can see some ships docked over there, around the entire site there's a big revetment, which is also a fire retaining wall. So it's a big systems problem. And the issue is if they lose oil off this site, at the time, 1980-ish, the they feared that the Japanese government would fine them about $1 billion in 1980 dollars. And the problem was this 10-meter thick layer of hydraulically placed loose sand, which was thought to be relatively susceptible to liquefaction. This is Tokyo. There's earthquakes. This was shortly after Alan Cornell had developed his probabilistic seismic hazard analysis approach in 1968, and Alan was down the hall from us, and so we stole that idea. We stole a lot of ideas. We stole that idea, and Bob and Mishak created a seismic hazard analysis of the site. But then we were faced with all this stuff that could go wrong. So also down the hall from us in the other direction was Norm Rasmussen. The name may mean something to some people. Norm has now passed away, but Norm was the director of the WASH 1400 study, the Nuclear Regulatory Commission probabilistic seismic hazard study of nuclear plants. And a bunch of their graduate students were in our classes. And so we stole their idea about using event trees to model the different things that could go wrong at this tank farm. And so this is one of the patios. This is the patio with those 4 big tanks in it. And we created event trees like that for all the patios. And eventually the thing kept getting bigger and bigger and got a little bit out of control. But this allowed us to not worry about trying to put numbers on what could happen to the whole site, but rather to, like engineers do, to break it up into little pieces, put numbers on the little pieces, and then combine them in a logically consistent way. So that's what we did. We broke up the uncertainties in a couple of different ways. This is the source of that tree that you may or may not have seen floating around various papers over the years on the components of data scatter and systematic error in soil property estimates. So that allowed us to kind of think about a taxonomy of where the uncertainties were coming in soil properties. The ones on the left-hand side were randomness in nature, aleatory. We call those things. In those days, we didn't call things aleatory. We just called them random. Now we call them aleatory. And the stuff on the right-hand side, those are the systematic or epistemic uncertainties. And then there were a whole bunch of uncertainties in all the pieces of this analysis, and we tried to break them all out. And we tried to sit around the table, the 4 or 5 of us, Bob Whitman and Alan and me and Mishak and sometimes Bill Lamb and some other people, and we tried to argue with ourselves in thinking, this has now become also a term of art, thinking slowly about where these uncertainties were coming from and how big they were, and trying to negotiate a consensus among us on what these numbers might be, because we didn't have enough data to actually do these things in a traditionally objective statistical way. 25 years later comes Katrina, and some of these people on this project are known to you. Marty McCann's known to many of you. Bob Pativ is still very active in the Corps. And the issue there was what were the risks in reconstructing what was then called the Hurricane Protection System for Louisiana. And it was the same kind of problem, and we thought we'd apply the same kind of methods. 20 years later, the models are more complicated. They're more systems engineering models. The uncertainties are a lot pretty much the same, and we use pretty much the same approach of slow thinking, consensus, breaking the problem up, and deciding as a group what numbers we were going to put on these various parameters. And again, there just weren't enough data to put numbers that were totally objective. So here's some lessons I think we learned from these 2 cases, especially from the Tonin case. The really important uncertainties, in my view, that we deal with in geotechnical engineering have nothing to do with randomness in nature. They have everything to do with what we don't know. I mean, the uncertainties are epistemic. They are not aleatory. Secondly, I'm going to say this again later. The statistics that we all learned in college are totally useless. Yeah, there you go. Okay. Yep. And that's fine, because none of us remember the statistics we learned in college anyway. And that sounds, that's intended to get a laugh, but I truly believe it. The statistics we all learned in college are sampling statistics. They're frequentist statistics. They deal with uncertainties, variabilities in the world. And that's not what we geotechnical engineers deal with. We mostly deal with how much do we know about something. We deal with epistemic uncertainties. And I've said before, and some of you have probably heard me say this, that in my experience, hydrologists, H&H people, hydrotechs, are all frequentists. They believe the world is random and we can use statistics to estimate it. Geotechs, in my view, are all Bayesians. They all believe in degree of belief probability, and uncertainty is in what we don't know about the world. And structural people usually don't care as long as the design meets code. Right? Third, this idea of dividing and conquering with models, that turns out later in life, I've learned that turns out to be replicated a lot of other places, not just in geotech. And this idea of thinking slow, deliberating, having a pencil in your hand, reaching a consensus among the experts is really important. And you know, nothing. We don't invent anything. So another fabulous reference, for those of you who haven't looked at it, is this recent bestseller by Daniel Kahneman, in which he talks about the advantages of slow analytical thinking over fast intuitive thinking, and you know, I mean, he won the Nobel Prize for that work, so it's probably worth reading. Okay, so what we learned from that. Next topic. So in Tonin and in Katrina, in the IPET, most of what we were doing was kind of seat of the pants, right? We were making things up as we went, trying to put numbers on judgment. But it turns out that there are formal protocols for doing this, and it's like election surveys, polls, right? The way you ask questions affects the answers you get, and the orders you ask them, and all that kind of stuff. And Roger Cook is a really famous academic in this field. He's an American who has taught in Holland for all of his career. And just about the worst way, it turns out, from all the research, to get a well-calibrated number from an expert is just to go ask him for that number, or her, right? That turns out to be a terrible way to do it. And by calibrated, I mean the following. If you come and ask me, I'm your consultant, you say, what's the probability, I don't know, that it's going to rain tomorrow, or that the unconfined, the undrained strength of this particular clay is blah, blah, blah. And I say, oh, 30%. Now, from a theoretical point of view, a Bayesian probability, a degree of belief probability, is true to the extent that it reflects your actual belief. And so Jean-Louis and he could put a number of 20% on this, and I could put a number of 30% on the probability. And if those numbers accurately reflected our respective degrees of belief, we would both be right. One of us would not be wrong, because we were truly stating those probabilities. But if I'm hiring him as a consultant, when he says 20%, I would like, if he tells me 20% a lot of times, I would like that in those times, about 20% of them turn out to be true, right? I would like him to be calibrated to frequencies in reality. So that's what I mean by calibrated. And it turns out if you just go ask people, you get terribly uncalibrated numbers, okay? So it turns out process is important, and there's a bunch of really good books that have been written in the last 20 years or so on these various protocols. And there are a whole bunch. Usually these protocols involve some sort of hypothetical betting situation. If you go back to the origins of subjective probability with a guy named Frank Ramsey in the interwar period, he axiomized the subjective probability approach based on the degree of belief reflecting people's willingness to take action when they were uncertain. That is, are people willing to bet on things, and if they are, that should reflect how sure they are that things will happen. And so there's a whole bunch of training aids and decision aids, you know, these spinning wheels that you can change the numbers of stuff on. These have been around for 30 or 40, 50 years, some cases. This is some work done by Bill Roberts, who was one of our students years ago at MIT, one of Herbert Einstein's students. And he works for Golders, and Golders has done a lot of risk analysis, especially in surface mining and in the oil and gas industry and in hazardous waste and other things. And So this is an example some years ago for FHWA where they used these spinning wheels, these probability wheels, to estimate various exceedance probabilities for the large-scale friction angle of a rock slope, and got their experts to estimate these exceedance probabilities in a variety of ways, and then at the end of the day can sketch a cumulative probability function through them. So this way of using formal processes and asking people what they would do in certain uncertain situations, this seems to work actually reasonably well, and experienced statistical research tends to suggest that the numbers are actually relatively well calibrated when you do things slowly using process. Needless to say, there are any number of software vendors who would be delighted to sell you interactive web-based software systems to do this, and some of them are actually relatively good. We use a bunch of them around the university. There's a citation at the bottom if you want to track that one down. And there's also this other issue, which is a relatively big one, which is if I have a group of experts and they all tell me slightly different numbers, how do I aggregate those into a single distribution? And there's basically two ways to do this. One is a sort of mathematical weighted sum kind of way. That's one that's been supported and argued by Robin Cook and a lot of the continental people who do this for things like dam safety and climate change policy. And the other approach is that's been mostly argued by Tony O'Hagan at Sheffield University, University of Sheffield in the UK, and that is to use group consensus, discussion, interaction, negotiation to reach a consensus. SHAC, the Senior Seismic Hazard Advisory Committee, was a USNRC project some years ago to try to develop a group consensus means of estimating seismic hazard for power plants. It uses this same consensus approach, and that is very much, in our practice, what seems to work better. We seem to get better calibrated, more thoughtful group probabilities by using discussion and consensus than using the more mathematical approaches. Much to the chagrin of many of my more mathematical graduate students, but that's Frank Plimpton Ramsey. Ramsey axiomized subjective. He was a student of John Maynard Keynes. He axiomized subjective probability. He invented the whole theory of discounting rating in public policy. He was the doctoral advisor for Wittgenstein, and he died at 27. Really, it's another one of these humbling biographies that makes you wonder what I've been doing all my life. As that old saying goes, when he was my age, he'd been dead for 45 years. Some things we learned. We learned that how you ask questions is important, that keeping it simple is important if you want to get calibrated results, that consensus and discussion gives you better calibration than just trying to mathematically aggregate, and that some kind of a formal betting or similar approach is really essential to getting well-calibrated numbers. And I'm going to come back to that in just a slide or two. Okay, so far we've had some experience at trying to do this. We know from research on a number of different fields that more formal approaches tend to give you better numbers than informal, just asking the expert approaches. But when you go and try to do this right, when you try to use all these good procedures, how good are experts and how well calibrated are they? I mean, are the numbers that experts give us, can we take them to the bank? Are they good enough to make decisions on the basis of? And this is a topic for a several-hour lecture all in itself, and I'm not even going to attempt to go there. We know from broad experimental work that all of us, people, are systematically biased in the way we associate numbers with uncertainty. It seems to be part of being a human. And there are several here that pop up in geotechnical practice all the time. The first one is that we are all wildly overconfident. Something I always do in my graduate risk class is I ask the class to estimate some number that they have no way of knowing. So I always ask them something like, estimate how many ships transited the Panama Canal last year. Now, we've worked there for several years, so I happen to know that number. Right? And now none of the class is going to know that number. That doesn't matter. And then I ask them to give me a bound, a 50-50 bound. A bound that you think has a 50% chance of containing the true number. And then I ask them, and while I'm doing this, you might be thinking in your head what that number is. How many ships transited the Panama Canal last year? And the third thing is I asked them to give me a max and min, right? What's the 1 in 99% bound? Man, you would be flabbergasted if the true number were outside that bound. Okay, did everyone have a number in mind? Quickly? Okay, the true number is 12,000. I'll try not to embarrass everybody, but can you just lift your hands if 12,000 was in your max min bound? Nobody? Well, if it were nobody, that would be surprising but not unusual. We tend to grossly overstate our confidence in things. The second thing is we tend to ignore base rates. If I go to the doctor and for my annual physical and I have a test for some intrusive test and it comes back positive, what's the chance I'm sick? Well, that depends on two things, not one thing. It depends on the false positive, false negative probabilities of the test, how good the test is, but it also depends on the incident rate, right? If there's 0 incidence of this terrible disease in the population that I'm part of, then it doesn't matter what the test says, I don't have it. So the inference depends on the false positive, false negative properties of the test, but it also depends on the base rate. And almost all of us tend to totally ignore the base rate when we're making inferences. Third is we tend to, all of us, especially geotechs, tend to underestimate the importance of sample size. So people go out, they take, I don't know, choose a number. They take 3 borings, they take 4 or 5 tests. They get a mean, they get a standard deviation on some soil property. And then they go out and they take another boring over there and they make another test and it's really quite different from the first 3 they took. What's the first response? My God, the geology must be different over there. Well, the geology is not different over there. It's just that when small samples have a lot of variability. And the chance that that one was like these is tiny. I mean, you should expect that that one's going to be different. We tend to ignore that. There's a whole bunch of other things. Steve does a great job of summarizing these. That's the Sheffield book. That's Roger Cook's books. And Shameless Commerce Division, that's John Christian's in my book. But all of those summarize these things if you're more interested. Okay. This goes under the rubric of taking your pants down in public. This is my personal calibration curve. Okay? And how do I know this? I know this because, this is going to sound like a total geek, but I routinely make estimates of probability of unknown things, and then I wait and see if they happen. And if they do or don't, I plot them. And along the x-axis is my subjective probability of various things happening. Could be geotechnical properties or parameters or events. Could be natural hazards like hurricanes. One of the events I just recently was looking at was estimating, putting a probability on what I thought the chances that Dorian, the recent hurricane, was going to hit the Carolina coast, where some friends of mine live. Okay? So I put a probability on those, and then I wait a few days and see if the event happened or not. Okay? And so I've plotted here my estimate of probability along the x-axis and the frequency with which things happened along the y-axis. So take a look at the arrow at 80%. So if I estimate something to have a 0.8 probability of occurring, the red line, typically it only has about a 0.65 chance of occurring. That's just empirical, right? And similarly, for rare events, if I estimate something at having maybe about a 0.2 probability of occurring, that is the red 45-degree line, on average, in my experience, it tends to have about a 1/3 or 30% chance of happening. So I'm reasonably overconfident, right? I estimate probabilities for likely things that are too high, and I estimate probabilities for rare events that are too low. I'm more confident. I'm exaggerating the probabilities. And you may look at this and say, oh my God, Greg is a terrible predictor. Well, yeah, maybe I am, but I'll tell you, this is not so bad compared to other people's calibration curves. I'll show you how I do that right now. So I was telling the two Annas, I live immediately behind the national Capitol in Washington, D.C., and so all my neighbors are staffers and congressmen and stuff, and so all the stuff in the Washington Post every morning is really in my face. So you may recall Brett Kavanaugh, maybe not. Just to refresh everyone's memory, he was the nominee for the Supreme Court, right? The last one, and spoiler alert, he did get confirmed. Just in case you don't remember that, he did get confirmed. So I was sitting around my breakfast table, and so I asked myself these questions. This is a few days. I was doing this actually every day, but a few days before the final vote, I said, if someone came to me, if Jean-Louis came to me and said, would you bet me that this guy's going to win the confirmation against me just flipping a coin, 50-50? And I'd say, oh yeah, I think he's going to get it. I'd certainly bet you if you asked me that. I would take it. And so I asked myself a whole bunch of other questions like this, and you can read through them. They're obvious. And I finally ended up with a couple of events. I thought the probability was more than about 2 and 3, and probably less than about 3 and 4. So I split the difference. I don't think you can get much better than that. And I said, about 70%. Okay, so he got nominated. I mean, he got confirmed, right? Was my probability wrong? Well, to the extent that probability reflected my true degree of belief, and in the sense that I was willing to, I mean, if you'd come to me, I would have taken that bet, right? So to that extent, no, I probably wasn't wrong. It was right. And so here's what you do. So this is the same chart. So I said 70%. So it's either yes or no, right? It's either 1 or 0. So I do this a bunch of times, I get a whole bunch of yeses. I do this a whole bunch of times, I get a whole bunch of no's. And basically, I mean, the fancy thing is to do some sort of logit regression, but you can just take a weighted average, across the x-axis, and you get that blue curve. This is something. If you try this will wake up your attention as to how good you are at estimating probabilities. And I'm going to move on to this in a second. I love this plot. This is from a guy named Richard Hoyer, who recently passed away, unfortunately. He was a colleague at the CIA with Sherman Kent. And between Richard Hoyer and Sherman Kent and Edwards Deming, I think you have to have a weird first name to be in this field, right? Because they all do. That was actually a joke, but that's okay. This is the experience of horse race handicappers. This is the amount of information along the x-axis. So they give them the daily racing form, they give them other information, they take them out to the paddock and they show them the horse before the race. So they give these handicappers various amounts of information, and then they ask them to predict who's going to win the race, and the vertical axis is the probability, the frequency with which they predict the right horse to win the race. And they average about 17%. Well, that's actually pretty good, because there's 10, 12 horses in a race, whatever. Their accuracy actually isn't very much affected by how much information they get. But their confidence in their prediction goes up dramatically as they get more. So if you give people more information, they just think they're getting better and better and better, and in reality, not so. So the answer is here, don't give your geotechnical engineers too much information, because they'll just be overconfident. It turns out that some people are extremely well calibrated. And the poster children for this are weather forecasters at the National Weather Service. That guy on the far left, that is Alan Murphy, the late Alan Murphy, professor at Michigan and later Oregon State. And he's famous for having worked with the National Weather Service for decades on their accuracy. And this is Glenn Briaud, who was then the director and had been the director for many years, and is famous for being very serious about the subjective probability estimates of their weather forecasters. And weather forecasters are right on that red line. They are really well calibrated. And the reason seems to be that they get a lot of practice. They do it all the time. They get feedback sometimes the next day, and management thinks it's really important. But they are empirically some of the best forecasters in the country. So that's good news. You can be a good forecaster with practice. Here's some more good news. You can actually train yourself to be a good forecaster, right? So these are some data from a guy named Douglas Hubbard, who's a project management consultant in IT in Chicago, and he wrote a book which I love. It's called How to Measure Anything. And in this, he did the same thing that I asked you to do with the Panama Canal. He asked experts to estimate uncertain quantities and then give them a 90% confidence band around it. And then he went and saw how many times people's 90% band included the real number. And so this is a binomial process. So the red curve, that's the calculated, that's the right, if they were perfectly calibrated, they should fall on that red probability density function or probability mass function. And so these light gray results, that's the first time he did the experiment with this particular client and the client's experts. Not so good, right? They didn't get hardly any right. They got 4 or 5 right, as opposed to, they should be getting 9 right. And so he went and put them through a whole bunch of training, and eventually, after a while, he got them up to this dark gray. So he got them to be actually pretty well calibrated. Now, it turns out that the Corps of Engineers does exactly the same thing in their dam safety program. They take their experts, from whom they're going to get elicited numbers, and they put them through training programs exactly like, they use exactly this one. They get them to estimate these numbers, they show them how overconfident they are, they give them some more practice, and they try to get these are mostly in-house experts, try to get them better calibrated so that when they go out and do dam safety appraisals, we might trust their numbers more. One last example. This is one Alan Marr talked about in April. This is Bill Lamb's MIT test section in Saugus, Massachusetts. This was an old test section that Federal Highway had paid for in the 60s, and the highway wars of the 60s left it unbuilt, and it was just sitting there, and Bill managed to convince, Bill, who's a very sweet-talking guy, managed to convince FHWA to loan him this embankment so he could load it to failure. And he did, and that's the failure right there. Okay? It actually failed symmetrically. It was really special. Alan was the project manager for this. And then he went out and he got 6 teams of experts from Berkeley and Imperial and Illinois and I forget all the other places. He gave them all the data they wanted and to get them to estimate the added height of fill till the embankment failed. And they did, and he got them all to come to Cambridge and present all the results. And in the meantime, in the intervening months, Alan and Bill and that whole crowd had loaded this thing up to failure and it failed. And so they had the data, which was kept secret, and they presented the data at the end of the conference. And so here's some interesting plots. These are plots from Mary Ellen Hines' master's thesis, and many of you probably know Mary Ellen. She was at the Corps for most of her career. On the left are the max-min bounds, you can think of that with the 90% bounds, if you will, of the experts. And the blue dotted line is the actual outcome, height to failure of the embankment. And you can see that only 3 of the experts had max-min bounds that included the actual number. So another example of people being really, really overconfident. This is the audience. They were a little bit more cautious. They were a little bit better. About 2/3 of them, the 90% bounds actually, or the max-min actually included the real number. The other thing to notice here, though, is that the average of both groups is actually pretty good, right? If you take the average of the 6 experts, there's 7 there because that top one is a bunch of MIT students. Their average is not too bad, and the average of the audience is actually pretty good. This is something that's been replicated a lot. There is wisdom, quote, wisdom in crowds, that when you get a bunch of people together to estimate numbers, their errors tend to balance out. Some people make one kind of error, some people make another kind of error, and those errors balance out. So there is wisdom in crowds, and usually a group of people is more calibrated than any one of the individuals within that group. The last one of these, this is from Steve's book. The data are from Baruch Fischoff at Carnegie Mellon. And Steve replotted, the data are in a table in the original paper. Steve replotted them. In this experiment, Fischoff and his colleagues asked a number of subjects to answer questions that were very obvious. What's the national language of Finland? And so you answer it, and then you are asked to say the probability you think your answer is wrong. well, I know the national language of Finland is Finnish. The probability is like 10 to the minus 4 that I'm wrong. Well, people actually aren't very good at estimating those small numbers. So this is the same kind of calibration curve I've been showing you, exactly the same. It's subjective probability on the x and actual frequency on the y. And you can see that people are not so badly calibrated for numbers above about 10% to about 90%. But once you get below about 1%, people are terrible. So to go and ask, as I've sat in many of these consulting meetings where experts are asked to estimate something in dam safety and people are throwing around numbers like 10 to the minus 4, you can't, those numbers are totally unbelievable. They're just, should I say, believe me, they're totally unbelievable. Okay, what have we learned about how good people are? And then I'll just have one quick thing and wrap up. How good people are. Cognitive biases are real, and if you're going to try to ask people to quantify their engineering judgment, you got to understand what those biases might be and how big they are and in what direction they are. All of us are really overconfident. That's just the way things are. We are. Probably, I don't know. I've always speculated that as we were evolving, nobody worried about probabilities of terrible things happening that had a 1 in 100-year chance of happening. We really cared about the lion that was in the bushes about to eat us. But we didn't really care about the 100-year drought because we were too worried about the lion, right? So it may be that we're just not wired to be well calibrated for these smaller events. It turns out that we can learn to be better calibrated, and that's the good news, right? It turns out that nobody is very well calibrated for small events, so the take-home lesson is if you're dealing with small events, you better break them up in an event tree or something, and so that they consist of a product of bigger events or probable events. And the teams are almost always better calibrated than individuals when putting numbers on judgment. Okay. A last and really quick example. This is just from this past spring. And this deals with a problem that has been, I think, interesting to me anyway for a long time, which is the nature of uncertainty in geology, not in geological interpretation. We have some geologists in the room today, as opposed to geotechnical parameter estimation. I love this. This is not new. This is from the paper was 1963. This is the same area of the Canadian Shield in eastern Canada, mapped in 1928 and 1958, 30 years apart. And you look at it and you say, oh, well, the maps are different. What's interesting is there were no new data collected in those 30 years, right? It's the same data. What had changed is the theory of granitization of the Precambrian Shield evolved in that period, and the Canadian Geological Survey, or whatever it's called in Canada, reinterpreted the same data in light of a different theory, and they come up with different conclusions. Everyone in the audience says, oh yeah, that seems reasonable. It is reasonable. But that means that we can't just go use the statistics of data to draw some of these kinds of conclusions, because the theory is hugely important in geological interpretation. And this brings me back to this wonderful book of the 1950s. Professor Meal got booed out of conferences after this book came out. He worked mostly in clinical medicine and in psychiatry, in clinical psychiatry. And he did a long series of studies on a comparison of how good clinicians were at subjective probability at their judgment, right, medical judgment, versus very simple statistical models like regression. It turns out that regression was a lot better, right? If you had a model and could interpret the parameters of the model as opposed to just making up, sort of intuitive reaction judgments, you could be much, much better calibrated. And this has been replicated all these things have been replicated a lot. The really famous guy who's replicated this is Robin Dawes from Michigan. And he published a paper also in clinical medicine called The Robust Beauty of Improper Linear Models. This seems to be really well documented too, right? Simple models perform much better. We don't want to hear this as professionals, perform much better than our raw professional judgment does. Okay, so let me just wrap this up. This is from earlier this spring. This is a little paper that's going to appear in Geostrata in the spring. That's the Franklin Bridge over Tampa Bay. That's Tampa to the east, to the left, and St. Pete to the right. And it's only about 20 feet of water. That's Tom Waits, that was part of our group. That's Ross McGilvery's fishing boat. He figured we'd get a little bit of fishing in while we were doing a site recon. And those piers are on relatively long pilings. They were concrete. This dam was built in 1991. The piles were concrete, pre-stressed, and they thought they would go to about a depth of 60 feet. And this is all basically limestone. It's very weathered, not very good limestone, but there are these limestone strata in there that are reasonably thick, 20, 30 feet, some of them. And the idea was that the piles could be driven end-bearing into those more competent strata, and those are blow counts to the left. You can see the blow counts are really high, and so that was the concept. And so they went out and they did a bunch of test borings, and the orange triangles, those are the bearing elevations, the pile tip elevations of the test piles. They did a lot of them, and that is St. Pete to the left and Tampa to the right. And when they went out for each pier, they put about a dozen piles under each pier, and the blue is the shortest pile under each pier. But the green is the longest pile under each pier. And so, this led to a claim and blah, blah, blah. And nobody expected those long piles. And some of those piles were really long. I mean, the pile here at 40E is almost 200 feet. There were some longer piles, by the way. The longer piles never did bear up, right? All these piles did eventually bear up. So what's going on? Well, what it looks like is going on from a geological point of view is some of the piles, yeah, they do bear up. In fact, most of the piles do bear up where you hope they're going to, but some of them, due to the spatial variation of those limestone strata, or due to the energy of the pile driving, or due to who knows what, punch through that layer. And if they punch through, there's almost no tip resistance. They become friction piles. And so those friction piles, they get driven twice as long until they bear up, right? And some of these things, these really long ones, we think hit some kind of old karst feature that was infilled with maybe under-consolidated materials. And they never did bear up. I mean, you can drive those forever. And so how do you make an estimate for they're building a new bridge now? How do you make an estimate of the uncertainty in the pile lengths and the pile costs, and in ordering the precast piles for the new bridge? Well, we thought it would be good to go back and try to build a model for this, and then put our judgment on the model. And here's what we found. Those sets of 10 or 12 piles, those are all the piles to the end-bearing ones. Those are the ones that set up just like expected. They're about the same length as the test piles. There were a bunch that punched through, and they were much, much longer. They became friction piles. And then there's a small number that never did bear up, and we associate that with karst, but who knows what the true thing is. So we came up with this little model, and this says that you can think, instead of trying to estimate this crazy, very skewed distribution of how long the piles might be, you can divide it up into 3 different kinds of piles, and then base your estimates on the model of the geology, and we think you can get a better estimate by doing that. So, jury's still out. This project is still going on, but here we tried to use a physics-based model of the geology combined with engineering judgment parameters. All right, so let's just wrap up. What we learned about geology, and this goes back some time, is that geological data, according to me, don't speak for themselves. They need to be interpreted, and that we use engineering judgment most effectively to adjust the geological model rather than just to intuitively make guesses at how much variability there might be. Well, there is a paper on this. I kind of got carried away this summer. This you can write forever. The paper ended up to be like a monograph. It's on the Civil Engineering Department website under my faculty name. If you want to get a copy of it, you can just download it. It goes into a whole lot of other topics. But just to sum up, here's what I think we've learned from 50 years of trying to put numbers on judgment. If you want to get numbers that are solid and well calibrated in the sense I've talked about, you got to take the whole process seriously. Just getting a bunch of experts in the room and asking them their probabilities is, in my opinion, doomed to failure. It's a process, and just associating words with these numbers is a very poor substitute for trying to take the process seriously. We all of us in this room, we are all subject to systematic cognitive biases in the way we put numbers on uncertainties, and the more we can learn about, there's been years of research on this topic, the more we can understand those systematic biases, the better we will be able, the more calibrated we will be in putting numbers on uncertainties. And we know that we can learn. People can learn. That's been documented. And lastly, it's usually better to have some sort of physics of failure-based model to organize your engineering judgment than it is just to intuitively make a prediction of the end number. And I'd like to finish with just this cartoon, which really spoke to me. We can thank Hippocrates for changing healing from an occult art to a science. But look at all we have to learn. Yeah, let's change it back to an occult art. Probably bad advice. So, thank you very much.
Now it's my pleasure to introduce Professor Rudy Bonaparte. Dr. Rudolph Bonaparte is board chairman at Geo-Syntec Consultants in Atlanta, Georgia. He's previously served as president and CEO for 20 years, building the firm to 1,200 employees in more than 60 offices in 6 countries. He's also a professor of practice in the School of Civil and Environmental Engineering at the Geo-Institute of Technology. Dr. Bonaparte received his bachelor's degree in 1977 from the University of Texas, his Ph.D. from the University of California, Berkeley. His practice focuses in geotechnical and geoenvironmental engineering. He is the author of more than 70 peer-reviewed technical papers and several book chapters on these topics. He is the recipient of the ASCE Opal Lifetime Achievement Award in Design, the ASCE Terzaghi Lecture Award, the Crows Medal, the Georgia ACEC Lifetime Achievement in Engineering Award. He was elected to the U.S. National Academy of Engineering in 2007. He is a licensed professional engineer in 17 states. More personally, I know Rudy as a very clever engineer, a magnificent politician, a great businessman, and most importantly, a wonderful person. The title of his Terzaghi lecture is Geotechnical Stability of Waste Fields, Lessons Learned and Continuing Challenges. Please welcome Professor Rudy Bonaparte.
Well, thank you, Jean-Louis, for that really very generous introduction. And Greg, you know, as you were describing how you felt intellectually compared to this 27-year-old student of John Maynard Keynes and everything he'd accomplished in a short life, just know I'm standing up here now feeling the same way towards you. So I was here in 2011 as the Buchanan lecturer, and really had a nice visit at that time. So when Jean-Louis invited me back, I was, of course, very, very happy to come here. And it's nice to see everybody. Thank you for sticking around. Title of my talk is Geotechnical Stability of Waste Fills, Lessons Learned and Continuing Challenges. So it's kind of customary, if you're asked to give the Terzaghi lecture, to share your sort of lineage back to Professor Terzaghi, and this slide reflects that lineage in my case. And for me, it's through the important academic mentors in my career, Roy Olson at the University of Texas as an undergrad, and Mike Duncan and Jim Mitchell, who were at Berkeley when I went through the program there. I'd also like to identify 3 other Terzaghi lecturers that were important in my career. Jean-Pierre Giroux, who for many, many years was my colleague, mentor, and friend at Geo-Syntec Consultants, and Dave Daniel and Bob Kerner, who both practice and do practice in the field of geoenvironmental engineering, and I had the chance to work with them on many projects through the years. The organization of my lecture is pretty straightforward. It's really a timeline with a beginning and end. We're going to take a look at the topic of landfill stability, starting back in the 1980s when modern landfills were first coming into being as a result of EPA regulations. And we're going to see there were a number of failures at that time. We'll see what lessons we learned from these early failures. We'll then fast forward to the current decade, and we'll see that there are continuing challenges. There continues to be a relatively large number of failures in the United States and around the world in these facilities, and we'll ask ourselves why and what lessons can we learn. And I'll conclude with a few observations of the standard of care for practice in the United States at this time. So why is this topic important or of interest? Well, the reason is there are many, many facilities in the country and around the world, and the consequences of failure can be significant. There are more than 2,000 active municipal solid waste landfills in the U.S. alone, thousands of closed facilities, many, many hundred coal combustion residual impoundments, mine tailing impoundments, hazardous waste landfills, radioactive waste disposal facilities, and many, many times that number as we look around the world. And the consequences of an unstable waste fill can be significant in terms of risk to loss of life, property, and environmental contamination. Not everyone here may be familiar with these facilities, so I've included this basic slide to just illustrate the different components of a modern waste fill. And we'll talk about some of these things in the various case studies we're going to look at. So this is a modern landfill. We see the waste mass here. The brown lines represent cover soil that's placed every day over the waste. Beneath the waste, we have a liner system. In this case, we're showing a composite liner, which is common in the U.S. today. And a composite liner has two components. We show a lower compacted clay liner, or CCL, and an overlying geomembrane. And this liner is meant to prevent leachate from the waste, liquid in the waste, from percolating into the ground and causing contamination. And above the liner, we have a leachate collection and removal system. So the liner blocks the liquid, and then the leachate collection and removal system, a granular layer here, allows that liquid to be collected and then pumped into a system for treatment. Above the waste, we show an intermediate cover soil layer here that's often placed before final cover is placed. And that final cover system will also typically include a geomembrane and other components. I'm also showing a gas extraction well. Landfills generate decomposition liquids and gases. The way we get these out are through these systems, through the gas extraction system and a liquid extraction system. So geotechnical design engineers involved in these facilities must be cognizant of multiple static and seismic failure modes that can exist at each stage of development of the project. And if we look at those, they include sliding through the waste mass itself, sliding through the waste mass and along liner system interfaces, sliding through the waste mass and the foundation soils. There can be stability concerns with berms and dikes around the perimeter of the facility. And then, of course, veneer stability failure, sliding at the interfaces of the liner system and the final cover system. Today, I'm just going to be talking about failure modes that involve sliding and movement through the waste mass itself. There's lots of information in the literature, lots of case studies about veneer failures, which tend to be fairly common. So where did we start? As I said, we go back to the 1980s when EPA promulgated regulations for municipal and hazardous waste disposal facilities. Those regulations caused the cost of these facilities go way up with the need for the liner systems and cover systems and all of those kinds of things. Facilities got bigger, taller, slopes got steeper, and so slope stability became a bigger concern. There were a number of notable failures during that time. A few of those are listed here. What I'd like to do is just highlight three of them and see some of the lessons we learned from these failures during the relatively early period of modern facilities. Well, the first such facility is the Kettleman Hills hazardous waste landfill failure in California in 1988. This involved a waste mass and liner system interface failure mechanism. What we see in the photograph here is the facility. This is the cell that failed. It's bowl-shaped with an open end at the bottom here. And here we see the waste mass in an aerial photograph shortly after failure in the direction of failure towards the open end of the cell. This is the liner system that underlaid the cell. It's a double composite liner. It was perhaps the most sophisticated liner system that had ever been constructed up to that point in time by a well-known and well-regarded engineering company. So it included a secondary clay liner, 3.5 feet thick, very low permeability, overlain by a geomembrane, and then a drainage layer, they called this a secondary leachate collection and removal system, and then a primary clay liner and overlying geomembrane, and then a primary leachate collection and removal system and various other layers. So quite thick, probably 8 or 9 feet in total, lots of interfaces between different materials, and as I said, one of the most sophisticated and most engineered liner systems that had been designed and constructed to that point in time. So about a year into operations in early 1988, after a year of filling, this waste mass here failed by sliding in this direction here about 35 feet. And the question is, why did it fail? It moved a large distance over a period of several hours. We got involved in the forensic investigation of this facility, and through that found that the mechanism for movement was sliding along liner system interfaces. Slippage was observed to be at the interface between the secondary high-density polyethylene geomembrane and the secondary compacted clay liner, and you can see that here. This is an area where the waste has been excavated. This is the secondary compacted clay liner. And the second geomembrane is being hidden by this geotextile, but it's right under the white geotextile. So sliding occurred at that interface. For scale, you can see a worker here standing just above the area that tore. So pretty large area liner. Testing, interface testing, direct shear testing that was conducted after the failure showed that the residual shear strength between the secondary clay and high-density polyethylene geomembrane, the strength was very low, on the order of about 500 pounds per square foot. Testing also showed that the geosynthetic interfaces were very, very weak, with interface friction angles typically less than 10 degrees. Now, at that time, we understood interface behavior was important, but people hadn't realized the strengths of these interfaces can be as low as they turned out to be. 3D effects were also found to be important, as was progressive failure of the system. So, as I said, interface testing was conducted. This just illustrates two sets of test results from that time. Geosynthetic and geomembrane clay. I think the important point I want to show is that for both of these interfaces, the peak shearing resistance occurs at a movement of only on the order of 0.1 inches, and after the peak strengths are obtained, there's a large drop-off in strength, so it's a strain softening type of material. So if you think about building this massive facility, placing these different geosynthetics and clay liners on a slope, and doing it without getting less than a 0.1 inch of movement at the interfaces during construction, you can see it's almost an impossible task. And this led us to understand that residual strengths in these kinds of systems, large displacement conditions, are really quite important. So what were some of the lessons from this first case study? First, that many liner system interfaces are weak and exhibit pronounced shear softening with residual strengths much lower than peak strength. Secondly, liner system construction and waste placement can and will typically induce movements that can result in post-peak shearing conditions and lead to progressive failure of these slopes if not adequately accounted for in design. Waste mass stability evaluations need to be conducted at each stage of facility development. This failure occurred at an interim waste condition, not a final waste condition. Given that many of these structures have many, many interim conditions over a period of a decade or more, it's important to understand that development sequence and to evaluate it as part of the design. Then lastly, geomembrane compacted clay liner interface strengths are sensitive to compaction conditions. Just about every type of compaction situation with clay materials, the resulting engineered structure is sensitive to the way it's compacted. This was particularly important here because it created a conundrum. We like to compact clay liners wet of optimum with kneading compaction and smooth rolling the surfaces to get low permeability for environmental protection. But those precise compaction conditions also result in low interface strengths. So what you want to do for environmental protection runs counter to what you want to do for slope stability. And those things, we now know those two things need to be balanced during design. Second case study from the early period is in Maine, the Crossroads landfill. This is from 1989. This is a waste mass and foundation soil failure. And we see the failed cell here. What happened is this cell underwent a retrogressive failure starting on the west side of the site. And you can almost see a whole series of slumps, waste blocks, and grabens as you migrate from the west side to the east side. This cell that you see here is 8 acres inside, and it is sitting on a foundation consisting of a very sensitive glacial-marine clay silt layer that's over-consolidated at the crust, and it transitions into basically a normally consolidated condition at a depth of about 20 feet. This is the Presumpscot Formation for those that might have worked in New England. The clay silt layer sitting beneath the landfill served as a liner. There was no constructed liner system or leachate collection and removal system. So after about 13 years of operation, with the waste height at about 70 feet, and after a period of heavy rain, a rapid retrogressive slide occurred involving about 650,000 cubic yards of MSW. So this was a big failure. This was a large failure. The sliding surface was determined to be in the normally consolidated zone of the clay silt layer, so below the over-consolidated crust. And as a result of the failure, waste blocks, the waste blocks we see in the photograph, moved as much as 160 feet from east to west. So, as I said, this facility had been in operation for about 13 years, and there had been some slope stability analyses conducted when it was first designed. And just a few months before the failure, another set of slope stability analyses were conducted with the hope of raising the height of the landfill. And the original slope stability analyses used vane shear tests to characterize foundation strengths. In the new analyses, the engineers made estimates of the amount of consolidation of the landfill under the weight of the foundation under the weight of the landfill, and they estimated shear strengths basically using a Shansep type approach. And with this approach to these new stability analyses, they calculated a factor safety for the landfill of 1.0. Whoa. So you might think they stopped filling the landfill, but they didn't. They kept filling, albeit at a slower pace. What they did do, I should also add that they were monitoring inclinometers around the perimeter of the landfill at the same time, and they were seeing movements shear movements in the normally consolidated zone averaging about 1.5 inches a month, which they characterize as high but acceptable. Greg, you were talking about optimism. There was optimism here, I think. So while they continued site operations, they started constructing stability berms around 3 sides of the landfill, the east, north, and south sides, but they didn't construct a stability berm on the west side. And why is that? Because on the west side, they wanted to make an excavation. In fact, they made an excavation on the west side. So they're building a stability berm on 3 sides and excavating on the 4th side. The excavation was for a new lined landfill cell. Well, what do you think happened to this landfill when they made the excavation? Failed. They unloaded the tow on that side, created very high shear stresses in this very sensitive soil, and it failed. It failed, according to reports at the site, at the toe with this rapid retrogression that resulted in the morphology, the slide morphology that we see here. So this factor of safety of 1 was interesting because what we also found out was they were more or less right with the factor of safety, but for all the wrong reasons. The unit weight of the waste that was used in the stability analyses was underestimated by something like 25%. So they thought the waste, in fact, the waste was much heavier than they thought. But on the other hand, they had estimated a shear strength that was much stronger than the actual condition. So things just seemed to fortuitously equal out. But in any event, the landfill failed. So what were some of the lessons from this case study? Both waste and foundation unit weights and shear strengths must be adequately characterized. And I really want to stress waste because up until this time, I think people hadn't really paid attention to the need to fully characterize the geotechnical characteristics of waste materials in these kinds of projects. And that came through loud and clear in this particular project. While I didn't talk about it, the forensic investigation showed that there were elevated liquid levels within the landfill. There was no leachate collection and removal system, and this contributed to the loss or the lack of stability of the facility. Another lesson we learned is that each significant construction activity or change in operations should be considered with respect to its potential impact on stability. So in this case, there was an excavation at the toe of the existing landfill, but there was no corresponding evaluation of the stability of the landfill with that excavation in place. And then clearly, from this, another lesson was a basic one for geotechnical engineering, and that's for soft soil sites where you're loading the sites. The rate of filling needs to be moderated or controlled in concert with the rate of strength increase in the foundation. So this is a classic staged loading geotechnical type of problem and geotechnical type of analysis that wasn't adequately characterized in this case. The third and final original case study is a waste mass and foundation soil failure in Ohio in 1996. This is the Rumpke landfill, and we see it in the photograph here. This is about a 20-plus acre area. It's a very large cell. The area that failed is to the south or above this line, which represents the original TOA slope of the landfill. So this is the part that failed. You can see this very large headscarp at the back of the slide. And you can see that the failed material flowed nearly 1,000 feet into this adjacent area. This too was an excavation for a new line cell. It had very little to do with this failure. but because it was an excavation and at a lower elevation than the failure, it contributed to the run out of this waste over a long distance. So the story of Rumpke starts in the 1940s when this family started dumping waste into ravines on their property directly onto an area that was underlain by clay, colluvial, and residual soils that formed a mantle over bedrock. So they really hadn't studied the geology of the area, and they're placing material into these ravines with this soil material filling the ravine. The landfill continued over many years until failure in 1996, and when it failed, the landfill had been filled to a height, to grades above what had been permitted. So both the clay material and the overfilling are important parts of the story of this facility. So they're going along, filling the cell, and at a certain point in the winter of 1996, about a week prior to the actual failure, the operator started noticing tension cracks up in the fill, and they started getting concerned that there were going to be problems, and they called their engineers out to the site. So they began monitoring the facility carefully, and movements continued to occur throughout the week, resulting in the day of the failure, an acceleration of creep rates, opening up of the tension cracks at the slope, and a progression of these activities to a point where failure occurred over a period of about 5 minutes, involving more than 1 million cubic yards, about 1.5 million cubic yards of material. So again, this was a very large failure that occurred over a very short time frame. This is an idealized cross-section through the failure area. And what we see is, this is the municipal solid waste. The light brown is the filling that occurred to the permitted grades. The dark brown is the overfilling that was conducted beyond the permit, so sort of, I don't want to say illegal, but it wasn't in accordance with the permit. There were high leachate levels, and you can see the geology with the colluvium native soil layer and the underlying bedrock. So the forensic investigation showed that the slip surface extended at a near vertical angle from the crest of the slope and then along the native brown clay out to the toe. Leachate levels in the investigation after the failure were found to be quite high, up to 30 to 40 feet. So that's a lot of liquid pressure acting in the landfill. Post-failure, shear testing of the colluvial soil produced fully softened and residual friction angles of the material of about 20 degrees and 8 degrees respectively. So fairly weak material, particularly in its residual mode. The analyses that we conducted after the failure to evaluate, help us understand the cause of the failure, resulted in operative shear strengths based on two-dimensional slope stability analyses of the material of about 12 degrees. And so what we think occurred is that we had a material that probably prior to filling was close to its fully softened shear strength due to the many, many years the soil sat close to the surface in these ravines at the site, and the loading caused by, or the loading induced by the waste fill, the shearing induced by the waste fill, drove the strength of that material below its fully softened value in the direction of the residual strength. Didn't need to get to the residual strength to fail. I already mentioned that this overfilling occurred, and this was another contributing factor to the fill. It created larger shear stresses and additional loads acting on the native soils. And finally, like the last case study, we think that this landfill was likely at a state of incipient failure, and the actual very specific time of the failure, not the cause of the failure, but very specific timing, may have been due to a road that had been cut a few weeks prior to the failure, right at the toe here, to get access around this excavation for the expansion. So we think we developed an understanding of the causes of this failure. And the root causes are a lack of understanding of the strength of the foundation soils, a lack of understanding of the liquid levels and their influence on stability, and inadequate consideration of the effects of overfilling. So a lot of lessons here. So in terms of summarizing the lessons from this case study, foundation conditions for old unlined waste fills must be thoroughly understood if additional filling, excavation, or expansion of the fill is planned. So I had this landfill, it was filled to grade, their expansion wasn't ready. What do we do with waste? We're getting all this waste in, our expansion isn't ready. Well, why don't we just go stack it up on the existing facility, but without real consideration of the potential consequences. Secondly, strain incompatibility between the municipal solid waste, which is ductile. If you look at the stress strain curves for MSW, it's quite a ductile material. And colluvial soil, which is quite brittle, can lead to uneven development of shear resistances, localized shear softening, and progressive failure. And we saw that here. Leachate buildup in old unlined landfills needs to be carefully considered. It wasn't in this case. And then, just like the last case study, operational activities at the site, the excavation in the last case study, the cutting of the slope to place a road in this case study may serve as triggers for landfills that are just about on the verge of failure already. So we quickly went through 3 case studies, and by the mid-1990s, we had learned a lot of lessons. In fact, I was asked in 1995 to write a keynote lecture about the state of the practice for landfill design. And I remember saying, you know, it comes back to optimism. We knew what we were doing, and you know, we had kind of solved this problem. And in hindsight, that was perhaps a bit too optimistic. But by that time, we had, in fact, learned a lot of lessons. Maybe we didn't learn. Maybe we learned the lessons, we didn't learn how to apply them consistently. And they're listed here. You know, the first one and the most important one, don't forget fundamental soil mechanics. And that applies to a lot of the things that we see. Waste materials have geotechnical properties. Liquid and gas conditions in the fill are important. They can create elevated pore pressures leading to failure. Soil and geosynthetic interface strengths are real important. You have to understand them, both peak strengths and residual strengths. Mobilized strength compatibility is often an issue. Progressive failure mechanisms must often be considered. Time-dependent stage loading response must be addressed at soft soil sites. These sound like things like building a highway embankment on soft soil. They're not that much different. Numerous interim waste configurations often require assessment. Well, this may be a little bit more unique to disposal facilities. Operating conditions in the field often deviate from the original design. Again, these facilities may have an operating life of 10, 15, 20 years. You design the facility before you start operations and then don't pay attention for the next 20 years. There's a good chance for something to change and go wrong. Surface cracking and toe bulging may be signs of incipient failure, and communications between engineers and operators are critical, in part because of these long design lives and the potential for things to change as you go along. So again, we learned a lot. So we're going to get in the time machine. Let's go forward 20, 25, 30 years and see how we're doing. Surely we're doing much better than we did some time ago. So I titled this section of the second section of the talk, Continuing Challenges, but could just as easily have titled it, So Why Do We Keep Having These Waste Fill Failures? And if we look at the current decade, which we're almost to the end of, waste fill stability failures have continued to occur on a regular basis. Just the ones I know about, substantial large failures, more than one per year in the United States alone. And you see a lot of these now have confidential next to them, and so we only know about them because we were involved in the forensic investigation. I'm sure if Geosyntec was involved in a number of forensic investigations, Golder or someone else may have been involved, and there are additional failures that we're not aware of. What I'd like to do again is select three that we were involved in and show you a little bit about each of those and what we learned, and then I'll be concluding. But I also want to stop at this point and make a broader point that while I'm only focusing on the US, this is really a very large problem around the world. In fact, in many developing countries, it's a much bigger problem than it is in the United States. It's not uncommon once or twice a year or more frequently to hear about a major landfill failure in a developing country that has killed tens or dozens of people and really had catastrophic consequences. And a few of those are illustrated in these photographs. And so this is an area where there's need for improvement around the world. And while I'm really focusing today's discussion on landfills, I also want to make the point that I think a lot of the same types of lessons that I'm describing here for landfills are equally applicable to other types of facilities, such as mine tailings piles, CCR impoundments, which is a big thing in the United States right now. And many of you probably know about the Kingston failure with TVA or the Dan River failure with Duke, and some of the recent tailing piles failures like Mount Poly or Valley, Brumadinho in Brazil. So I think more broadly than just MSW landfills, the kind of thoughts and lessons I'm sharing applies to the broader universe of waste-fill facilities. So let's go on to the three failures quickly here. So this first one is a confidential MSW landfill in the eastern US, and this involves a waste mass and intermediate cover soil interface failure. We see the landfill here, it's about 190 feet high, and here's the failure, obviously. Here's the crest of the slope, and here's the toe of the slope. So this is the edge of the landfill. So you can see the waste in this case ran out quite a long distance. In fact, it carried more than 500 feet across relatively flat ground. And so one has a sense that this material truly liquefied. So at the time of the failure in September 2011, waste filling had recently been completed and a landfill expansion being built over an existing landfill. So think about this. There's an existing landfill mound and it's all filled. The owner wants to keep filling at his site. So he looks around and he says, hey, I can build 100-foot wide, I can extend my liner system 100 feet and then build this veneer up on both sides and get additional volume. And that's what he did. And it was that veneer that actually failed. This was a very wet landfill, very, very wet. It underwent heavy leachate recirculation. And what that means is leachate that's collected in that leachate collection system I showed at the beginning, and they pump out. Rather than taking it to a wastewater treatment plant, they bring it up to the top and put it back in the landfill. So it makes the landfill wetter and wetter. And you say, why would they do that? And they do it, one, it saves money. You don't have to treat the liquid. And two, it helps to biodegrade the waste more quickly, generating gas, which is an asset, something they can use, and allowing the landfill to settle more quickly. And as it settles, it stabilizes, and it's easier to put the final cover system on. So, you know, a little bit of recirculation is good, a lot isn't. I have a friend in the industry that says we're learning to drink responsibly. So it's, you know, like if you drink too much beer, you don't feel good. If you drink too much leachate recirculation, the landfill's not going to feel good. In addition to that, there was this facility really didn't do a good job getting their stormwater off of the landfill. A lot of that percolated in, and finally they accepted dewatered municipal sludges, and while they're dewatered, they're still quite wet and they're quite weak. So there were a whole series of operational things here that made it a very wet landfill. Failure occurred in the expansion area, that veneer in a matter of minutes and involved about 160,000 cubic yards of waste that flowed, as I showed, about 500 feet beyond the limit of the liner system. The post-failure investigation showed that the slip surface was at the interface between the expansion area and the underlying landfill. So the landfill, before they built this expansion, they put like a 2-foot low permeability soil layer, an intermediate cover soil layer, which I showed in the earlier photograph, over the landfill. And then they built the expansion on top of it. But they didn't take out that clay layer before laying the expansion up against it. And that's going to turn out to be very important. As part of the forensic investigation, we did a number of CPTU soundings around the perimeter of the felled area. So I should mention that all of these areas as well have this same veneer. So when we were retained, it was to not only investigate this failure, but to help the owner understand whether these adjacent areas were at risk of failure, and then develop a remediation plan for this. So when we went out, we did a CPT testing in these areas here after we'd gone through a safety assessment with a lot of protocols in place. And we found in these adjacent areas high piezometric levels. On-site observations the day after the slide revealed leachate pools and gas vents within the failure area, high liquid pressures, high gas pressures in the waste. That explains the liquefaction of the material and how far it flowed as it failed. And clear evidence of leachate overland flow in this area out here, again indicative of liquefaction of the material. Here's a cross-section idealized through the slope. This is the original landfill, the dark brown. This is the expansion. You see the liner system extended out 100 feet. And then the filling over about 18 months of this veneer. And here is the intermediate cover soil layer, the 2 feet of clay. And again, it wasn't removed. So if you have leachate in this area and it wants to percolate down to the leachate collection system, it really can't do that. So previewing a lesson learned is in this situation, you either need to take this layer out to make sure you can get vertical drainage, or put a new leachate collection and removal system on top of this slope, and neither of those were done. And this just illustrates the morphology of the slide mass after the failure, and this is based on survey, and you can see the large distance that it flowed out. So we, again, conducted slope stability analyses for this project to try to understand better the causes of the failure and what happened. And we used the CPT-derived piezometric levels in those analyses. And based on using a factor of safety of 1, we back-calculated a shear strength for the waste characterized by an effective stress friction angle of 26 degrees with a very small cohesion. At the same time, we took samples estimated to be about 75% municipal solid waste and 25% sewage sludge. Remember I mentioned that they disposed of that material in the expansion. And we sent them to Ed Kavazanjian at Arizona State University, who has an 18-inch diameter direct shear box for testing waste. In fact, he built it when he was with Geosyntek along with Dr. Bob Backus, and we used it on a number of projects. And when Ed went off to Arizona State, we said, take it with you. And he did, but he's still testing, and we had him perform the tests, and we generated friction angles in the range of 20 to 24 degrees. Now, what's the significance of that? We consider municipal solid waste to have a typical shear strength characterized by friction angles in the range of 32 to 35, 36 degrees, even at relatively high normal stresses. So in having these results, it's indicative of a material where the strength has been reduced by the presence of the sewage sludge and that's probably the dominant thing, and perhaps to some degree by the decomposition of the material that was occurring in this very wet and hot landfill. So some lessons here. Excessive leachate recirculation and stormwater infiltration can lead to the buildup of elevated liquid levels and poor pressures in the waste. Vertical expansions that involve the placement of new waste over old need to account for the interface conditions between the old landfill and the new landfill. In this case, this intermediate low permeability, intermediate cover soil layer was an impediment to vertical leachate percolation. So the lesson here is that in these circumstances, that layer either needs to be removed, as I said before, or a new leachate collection and removal system needs to be installed. We also, at this time, were becoming increasingly cognizant of the fact that these very wet landfills with leachate recirculation and other things are really poor conductors of gas. So you have this landfill with all this waste biologically degrading, creating lots of landfill gas, methane and CO2, and it can't get to the gas wells, and the gas wells are getting watered out because there's so much water in the facility. So you're building up gas pressures within the landfill, and so this is a great challenge as well. And finally, the effects of sludge on the strength, permeability, and degree of saturation of the waste must be accounted for in design. So a lot of lessons learned with this case study. This next more modern one is in the southeastern U.S., and Rodolfo Sancio from our firm, who is here today, played a major role in the evaluation of this facility. This was a waste mass and foundation failure. We see the slope that failed here. You can get an idea, it's about 90 or 95 feet high at a 4-to-1 inclination, so not remarkable for a landfill slope, not particularly high or steep. You see the back slope and graben that was formed after movement of the slide material. So the story with this one is that this landfill cell that we see here was constructed in a deep excavation, roughly 45 to 60 feet deep, depending on where you were, into a very highly over-consolidated native fat clay. So they excavated all this material for purposes at the site, uses cover soil, building berms, and other things. They made this big excavation. This excavation occurred in 1996, and the liner system in this cell wasn't constructed to 2007. So for a decade, stormwater ponded in the cell bottom. Might that be of interest? We'll see in a minute. So deep excavation, open for a decade, water ponding in the bottom. Waste filling occurred from mid-2007 to early 2009, creating the slope that we see here. And there was a liner system beneath this facility, but it wasn't involved in the failure, so I'm not going to talk about it. The failure itself involved translational movement that occurred in February 2012 over a period of several days. So think about this slope just really translating from east to west in this photograph here. And I should point out that on the west side, the excavation extended beyond the toe of slope. So it wasn't like the other side of the excavation was here. There was a soil buttress, but a relatively small buttress to demarcate the end of the cell. It was generally relatively open. And this failure occurred 3 years after filling was substantially complete and after a period of heavy rainfall. But the failure didn't occur immediately after the cell was filled. It sat there for 3 years before it felled. So all this is sort of providing clues as to what happened in this case. We see the cell here. Here's the headscarp. This is about 1,000 feet in length, so pretty large facility. Here's direction of movement. Here's the location of that intercell berm I just mentioned. You can see some bulging at the toe here. And here's some fairly large construction equipment to give you a sense of the scale of this. So the first sign of a problem occurred 3 months prior to the failure when north-south oriented cracks developed in the eventual location of the headscarp, so up in this area. So what do people do when they see cracks in the earth? They fill them with more soil, but then the cracks reopen typically after rainfall, and they would refill them again. So the slide involved a translational movement of about 700,000 cubic yards of material, a large volume of waste and soil, a distance of about 25 feet, as we see on the slide. The forensic investigation led by Rodolfo concluded that the failure mechanism involved shallow translational movement in the native clay beneath the bottom of the liner. I'm going to back up here. So we got involved in this investigation, as I said, and a number of piezometers were installed, a number of slope inclinometers, soil borings were advanced, and Shelby tube samples were obtained. The piezometers in particular weren't installed to a number of months after the failure, and by and large they were installed outside of the footprint of the failure because the owner was concerned about punching holes through the failed cell because there was a belief based on the nature of the movement that the liner system was still primarily intact, and there was a concern if you start punching many holes through the liner, you could be creating an environmental problem, and the goal was to avoid that. So unfortunately, we didn't have good information on the pore pressures in the failure zone at the time of the failure. Nonetheless, proceeded with the investigation. There was a large amount of laboratory testing conducted, triaxial testing, torsional ring shear testing, direct shear testing, compressibility, and other things. This just shows a few of the results. These are torsional ring shear results to evaluate the residual strength of the native material. And from these kinds of results, we generated strength envelopes for back analyses with an effective stress residual friction angle of about 6.7 degrees for this material and a fully softened shear strength of about 13.1 degrees for the same material. Talk about this in a second. I will note that these two strength values, based on their index properties, correlate fairly well with the correlations developed by Professor Tim Stark and his students up at the University of Illinois. So without a real good handle on pore pressures, we approached the stability analyses as follows. We reasoned that after this 25 feet of movement, the shear strengths along the slip surface were at residual values. After all that movement, they were at their minimums. And so we would know that. We knew the post-failure geometry and the factor of safety associated with that condition. And from that, we back calculated a pore pressure coefficient for this material of 0.14. We checked that pore pressure coefficient against some consolidation analyses to evaluate it for reasonableness. It seems kind of low, but if you think about it, this cell only had a clay liner, which was only in the range of 5, 7, 8 feet above the failure surface, with a sand drainage layer in that. And so the sand drainage layer actually served as a drainage boundary for consolidation purposes within the cell itself. And with that consideration, we thought this pore pressure coefficient was fairly reasonable. We then applied this pore pressure coefficient to an analysis of the pre-failure condition, the geometry of the slope before failure, with, again, a factor of safety of 1.0 to calculate or at least estimate an operative strength for the material at the initiation of failure. And we came up with a strength of about 10.6 degrees. So lower than the fully softened shear strength, but higher than the residual shear strength of the material. So putting all this together, we think what happened here is that the decade-long open excavation allowed ponded water to infiltrate the native clay through desiccation cracks, sickened sides, and soil suction due to the unloading and rebound of this highly over-consolidated material. This led to swelling and softening of the clay and fully softened shear strength conditions in this material close to the bottom of the excavation. Remember, it was open over a period of a decade. So you have this material with a shear strength around its fully softened value. Then you start filling the cell, it has slopes, you're inducing shear stresses. And these shear stresses generated by filling induce deformations in the native clay, leading to the progressive strength loss and ultimately failure. So a progressive failure of this material that was initially softened by the excavation, rebound and swelling, and then shear deformations induced by loading. So with that, I think the big lesson here is that geotechnical fundamentals matter. This seems like a classical kind of maybe grad school level geotechnical take-home problem to give a student, see if they would track this through. And the specific lessons with respect to soil behavior are those I just described. So the last case study, modern one, occurred in 2017 in the Northeast US, and this was completely a waste mass failure. And we see the failed area here. For scale, here's a tractor trailer, and that's a truck cab. So you get a sense that this is a pretty large failure. It involved 15 plus acres of waste, and unfortunately, very sadly, resulted in a worker fatality. So for this facility, in the weeks leading up to the failure, surface cracking, slope bulging, leachate seeps, and gas venting were all observed. So all of the indicators that something bad is going on. The owner became cognizant of that, and they did their best to try to investigate what was going on. And they actually got contractors out there to start doing things, but it wasn't enough. The failure occurred over about 10 minutes, so another very rapid failure, starting with the bursting of these bulges in the outboard slopes of the landfill, which then led to a larger slide, which released about 200,000 cubic yards of waste that again flowed several hundred feet, like one of the earlier case studies. So the waste again liquefied. And this seems to be, we've seen this at other facilities as well, so something that's become relatively common, telling us that some of these landfills in the modern age are too wet and have too much gas in them and aren't being managed sufficiently for those conditions. So this is an aerial view after the failure. All of this is failure area here. This is kind of the limits of the failure and the run-out area for the waste. You see two arrows because the face of this cell actually was like this. It was not quite a 90-degree angle, but close to it. And so, interestingly, both faces burst at about the same time, and you had one failure go in this direction and one failure go in this direction. The area where the failure occurred involved an expansion of a new waste cell against the intermediate slope cover of an older portion of the landfill. Does that sound familiar? Again, a veneer stability. The intermediate cover soil for the original landfill consisted of cuttings from oil and gas production, oil and gas drilling in this area, think Marcellus Shale type country, that they mixed with lime prior to placing it as cover material. So it resulted, once it set up, once it cured, it resulted in a hard, relatively impermeable, and relatively smooth intermediate cover soil layer. And again, as in the previous case study, there was no removal of the layer or installation of a new LCRS. In addition to the MSW, the landfill accepted a variety of special waste, including a sludge material that was characterized as low shear strength waste. And so that would, I think that would get your attention if you're disposing of low shear strength waste. The operations plan for the landfill required the LSSW to be placed in the interior of the cell. So these are all borings that were advanced and CPTs that were advanced as part of the forensic investigation. And the areas in brown are the areas of highest low shear strength waste. And as you can see, they're set back from the slope face. And this is that angle I was talking about earlier. So the idea was to set the low shear strength material in the middle of the landfill, not near the edge, as a way to improve the stability of the cell with this material in it. If it's in the middle, it's more stable than if you put it near the edge. And so that's a good idea. They're trying to do the right thing, but there were some unintended consequences. The setback due to the setback, all of this area was MSW. And it turns out with the filling rates, all of the MSW was getting used to create the setback, meaning that there were even higher levels of low shear strength waste behind the setback. So this is an unintended consequence of what was meant to be a very good idea. And I think one of the things that I learned in really thinking about all this stuff is unintended consequences. When you're doing something a little different, you really need to think about whether there will be any unintended consequences of what you're doing, and there was one here. So this resulted, obviously, in an interior zone with high LSSW contents, and ultimately a weak zone through which shearing occurred. And in fact, while the landfill only accepted about 20% of this low shear strength material, in these zones in the back, dark brown areas, the low shear strength material had concentrations or mass fractions of 40 or 50% or more. And that's important because we conducted testing on the material. Here is municipal solid waste, degraded municipal solid waste, and here is the low shear strength waste. And you can see this looks like a sludge or almost even like an axle grease. So representative samples of these material were obtained and sent to Colorado State University, where the faculty there have about a 12-inch diameter direct shear box that they use for waste testing. And the tests were conducted on mixtures of material ranging from pure MSW to essentially pure low shear strength waste. And you can see how the strengths vary as the percentage of low shear strength waste goes up. When you get in the range of 50% low shear strength waste, you can see your strength is highly degraded from typical municipal solid waste, which is reflected in this line here. This is the strength relationship Ed Kavazanjian and I developed back in the mid-1990s for MSW. So the mixture of this low strength material into the waste was one of the root causes for the failure, coupled with the inability to manage leachate and gas levels within the cell. So the lessons here were that special waste can create operational problems. Procedures developed to mitigate the problems can have unintended consequences. We saw that here. Special waste, if placed at too high a mass fraction and if not thoroughly mixed with MSW or other stronger waste, will create weak zones that adversely affect waste fill stability. And then, once again, low permeability zones in the waste, e.g. from special waste or intermediate cover, trap liquids and gases in the waste fill, causing fluid pressures to become elevated. So, to wrap up, to bring all this together, what does it mean? So first, we are relearning many of the lessons first learned 25 years ago, and this is the same slide from earlier. And I think the real question is why? Why are we relearning it? Is it that every generation of engineers needs to relearn things for themselves? Is it that the lessons aren't being passed down clearly enough? Is it that owners feel like they've been at this a long time and they don't want to pay for good engineering to be done? I'm not sure, but we're clearly seeing a lot of the same issues that we saw a long time ago. And then more recent lessons learned. We saw that aggressive leachate recirculation can saturate waste and cause high piezometric levels. Gas well collection efficiency is substantially diminished in very wet landfills. High moisture content landfills can lead to elevated temperatures in some cases. I didn't talk about this, but this is a big deal in the profession right now. Co-disposal of sludges and special waste can lead to stability and other problems. And vertical expansion configurations and materials have contributed to wasteful failures. We need to be cognizant of those interface conditions. And so I've just submitted a paper to the ASCE journal on this lecture, and in the paper I go into some detail on some of the specific measures that can be entertained or implemented for each of these. I'm not going to go through them here in the interest of time, but they're in the slides that I've provided, and if my paper gets accepted, they'll be in the paper. And I want to wrap up with this slide, my last slide. I now have great trepidation about showing this slide with Professor Baecher in the audience. And I'm not an expert in this area, but I think this is interesting, and I hope the way I'm using this doesn't get too much criticism. But I'm wrapping up with a comment about the standard of care in engineering practice. And the standard of care is a legal standard when you become a professional engineer and you're out practicing in the community that you'll need to meet if you're not going to get sued for negligence in your practice. And the standard of care is doing your work in a way that other engineers working in the same area contemporaneously in the same locale, faced with the same facts and circumstances, would conduct their work. And if you're ever sued, there'll be experts on both sides saying whether you've met the standard of care or not. So it's an important, in professional practice, it's a very important consideration. And I'm going to talk about that in the context of this graph, which I've adapted just slightly from a paper by Silva, Lamb, and Marr in 2008, Probability and Risk of Slope Failure, and it's a well-known paper. And in it, they used expert judgment and a variety of techniques, a few of those that Professor Baecher talked about today, to come up with relationships of annual probability of failure versus factor of safety for earth structures, really focused on embankment dams. Now, importantly, they characterize something called the level of engineering. To me, the level of engineering is the standard of care. They're the same thing, essentially. And what they said is that the level of engineering is typically associated with the nature of the project you're working. So for the most critical projects, the most expensive projects, the projects that have the highest consequences of failure in terms of monetary loss or loss of life, they do typically, and they need to have, the highest level of engineering. And that would be category 1. And you go through in 2 and 3, and category 4 is almost no engineering, and it would typically be associated with structures that have relatively low cost, very low consequences of failure. Applying category 4 engineering to a category 4 kind of engineering situation would more or less, in my mind at least, be consistent with the standard of care. Applying it to a category 1 structure would be gross negligence. So the thing I like about this plot is it ties the level of engineering to the facility characteristics. And in the paper, they talked about their notion, their sense, their conclusion that for the average earth dam design, and this would be an embankment dam, the average probability, annual probability of failure for a facility with a factor of safety of 1.5 would be about 1 times 10 to the minus 4, 1 in 10,000 on an annualized basis, which is, I think, the number. And then for the most critical structures and the best design, the probability might be in the range of 1 times 10 to the minus 6, or 1 in a million. And so this gives you a sense of their thoughts about the probabilities associated with these two levels of engineering. So I have a small database. We know there are 2,000 active landfills in the US, and we know that there have been, more than a dozen landfill failures we know about. We can use, no, it's not statistically robust, Professor Baecher, but we can use that data to make an estimate of what the probability of failure and the level of engineering is. And when we do that for waste fills, municipal solid waste landfills in the US, oops, let's see, here we go. We come up with a value of 1 times 10 to the minus 3. It's 1 in 1,000. That's a 10 times higher probability than the average earth dam. So we're saying the current state of practice in the US results in an MSW fill with a 10 times higher probability of failure. Now what you might ask is, are the consequences of failure similar? Does this make sense, or is it too low? And I'll get to that in just a second. I also want to just say that, you know, if you take any individual facility, it may fall anywhere along this line. It doesn't, and I'm not saying, just want to be clear, we're being recorded, all facilities don't fall at this point. Facilities probably don't fall at too much higher a probability because of regulations in the United States. You can't go too low in your design because regulators won't let you. And some facilities, I'm sure, are much better designed than that average, so there's a range. And I lastly want to say that I think this is my personal expert judgment after today. I think it's probably optimistic, but I've been deeply involved in the design of several Department of Energy radioactive waste disposal facilities where the level of engineering is very high. The quality control standards, the documentation standards, you know, the probable failure mode analyses you need to do. I think that, you know, you could say that these waste fills are up here with conservative earth dam design. So the full picture has a lot of components to it. And so to go back to this question of consequences as the last comment, I don't think every landfill has the same consequences of failure of every dam, but there are lots of landfills that have very, very substantial consequences of failure, very high financial consequences of failure, maybe higher than many dams. And so I'm not so sure it should be that different. And so, and if that's my conclusion, my parting comment is a call to our profession and to the owners of these facilities and regulators for us to work to try to bring the standard of care in our practice from here up, you know, at least to some degree up towards a level 2 engineering standard. So I'll leave you with that thought, and with that I'll say thank you, and Professor Briaud, thank you very much for inviting me to be here.